Hello again. Before moving on, I wanted to remind you the big O notation and also wanted to give you a few definitions about the algorithms that we are going to work on. So let's start with the big O notation. Big O notation represents efficiency of an algorithm, time factor of an algorithm, and space complexity of an algorithm. So this is why when we need this notation, because we are going to talk about time complexity or memory complexity or data complexity of an cryptanalytic attack. It is represented by On, where n is the number of operations. Note that big O notation disregards constants. For example, if an algorithm requires c times n cube steps, where c is just an integer, or actually it doesn't have to be an integer, it can be a constant real number. We write O(n) cube instead of OC times n cube. So we disregard the c, but of course this doesn't mean that that constant is not important. In some algorithms it really affects the running time of the algorithm, but we don't write it in the big O notation. An example is the constant time algorithm. So when we say O1, we actually mean a constant time algorithm. Here's an example. This function, where it takes an input as some array and an integer, but at the screen it prints the tth array, value of the array. So it is just a single operation. So this is why it is O1, because we can directly access an element in an array. Thus, regardless of the array size, this is a constant time algorithm. So that is the idea. It doesn't matter how big the array is. So let's look at On. We take the same input, but this time we print on the screen every array value starting from 0 to t. So your input t actually determines the running time algorithm. So, and here we assume t is the size of the array, by the way. So if t is equals to 100, an array of 100 elements will take twice as much time compared to an array of 50 elements. Thus, complexity increases proportionally. So this is the idea. So you can replace t with n if you prefer, but we have an array of size t. And this algorithm, because of this for loop which runs for t many times, is just OT or ON in the big O notation. So we have some sorting algorithms which are ON square. So if you have an array of n elements and you want it to be sorted, then it takes ON square time when you use these sorting algorithms. But average complexity of bubble sort is also On square. However, average complexity of quick sort is On log n. This is very important because this number is really small compared to this. And actually, in practice, I observed this in an experiment myself. When we are working with small n, people wouldn't mind if you are using quicksort or bubble sort, because both of them are polynomial time algorithms, so you get the result instantly. But if n is huge, in my case, in an experiment, I sorted 32 gigabytes of elements. So with bubble sort, I waited for a few hours, but I didn't get the result. But I moved on to quicksort, and the sorting took like 10 minutes or something. So it is the don't forget that big O notation gives you kind of an upper bound. Average complexity is also important. So let's look at On factorial. This is an example is Turbulent Salesman problem. Given an input matrix of distances between n cities, the problem is to determine if there is a route visiting all cities with total distance less than k. So this problem is somewhat hard. This decision version of the Turbulent Salesman problem is in NP, non-deterministic polynomial time. This means that you cannot solve every instance of this problem in polynomial time. So this is a huge open problem. People are still trying to prove is if NP is different than P or NP equals to P. but it is beyond the scope of this course. So here's a graph. As you can see, we have constant time or logarithmic time algorithms. For instance, binary search algorithm is a logarithmic time algorithm, so you can easily search a value in a sorted table. Polynomial time algorithms are here, O n log n here, n square here. Exponential time algorithms here, and when you move on to the factorial, it becomes, it converges to infinity very fast. So here is the number of elements and the number of operations you need to perform. As you can see, with these kind of algorithms, it doesn't matter how big the space, the array size is, you can still perform this many operations in reasonable time. But for exponential time algorithms, it is not that easy. For instance, the exhaustive search attack is an exponential time algorithm like here, because when the key size increases, the attack becomes harder and harder, as you can see in this graph. So here you can think n as the number of bits of the secret key. So let's look at a few types of algorithms. We define the polynomial time algorithms as follows. An algorithm to perform a computation is said to be polynomial time algorithm if there exists an integer d such that the number of bit operations required to perform the algorithm with a k-bit input is O k to the d. And the exponential time algorithms, which takes a lot longer time than polynomial time algorithms, is defined as follows. An exponential time algorithm has an estimate of e to the power c times k, where k is the total input length and c a constant. So you might think that sometimes polynomial time algorithms might be worse than exponential times because this d might be some really huge number, but exponential time algorithms, when the k increases, would be harder to, would require more operations to perform than polynomial time algorithms. So our aim is always to get a fast algorithm, so our aim is to find something in logarithmic time or polynomial time. So polynomial time algorithms are good, exponential time algorithms bad. So do we have something in the middle? And the answer is yes. We call them sub-exponential time algorithms. But before defining that, let's see an exponential time algorithm. We give the example as the trial division. Our aim is to find a non-trivial factor of an odd integer n by trial division. This is important because if we can find a polynomial time algorithm for this problem, you can break RSA encryption algorithm. So easiest way, most trivial way to do this division is to try all integers in the range starting from 3 to square n. Actually, you don't have to use all integers but prime numbers, but for this example, assume that we don't know, we don't have a list of prime numbers less than square root of n. So we try every number starting from 3 to square root of n and check if one of them divides n. So let's say that the number n that we are going to factorize has k bits. It's a k-bit integer. Number of trials are approximately square root of n because we are going to perform this many operations. And square root of n is, since we defined k like this, it will be 2 to the k over 2. And division of a k-bit integer with a k over 2-bit integer is of O k square. It is a polynomial time algorithm, the division algorithm. So since we are going to perform this many operations and each operation requires this many operations, final result is this big O, 2 to the k over 2 times k square. So it is an exponential time algorithm. So since this is an exponential time algorithm, you cannot easily factorize huge numbers, and this is why RSA is secure. But of course, this is the trivial version of trivial way of trying to factorize a integer. Question is, can we have a better algorithm so that it is not exponential time, but polynomial time. So far, nobody discovered the polynomial time factorization algorithm, but there are something in the middle between polynomial time and exponential time algorithms, and we call them sub-exponential time algorithms, and we define them like this. So there is big O notation like this, but we have two inputs, gamma and c. So sub-exponential time algorithms are defined like this as gamma c, and they're equal to big O notation e to the c k to the power gamma times logarithm k to the power 1 minus gamma. And c is a constant, so it can be anything larger than 0, but gamma is something between 0 and 1, and I will explain why this is the case. If k is the input size of an algorithm, and if the estimate of the time cost of the algorithm is L gamma c, with gamma between 0 and 1, the algorithm is called a sub-exponential time algorithm. So the value of gamma actually here represents how fast this sub-exponential time algorithm. So you can observe that since it takes values between 0 and 1, let's look at what happens at the boundary. So assume that gamma equals to 1. So when you write gamma equals to 1, this becomes 0. So ln to k to the power 0 becomes 1. We cancel this out. And since gamma is 1, this also cancels. So we end up with e to the ck. So when gamma is 1, we have an exponential time algorithm. But when gamma is 0, this k cancels, so you end up with e to the c times ln k. And since this logarithm is to the base e, the k will come to the bottom and c will stay at the top, so you end up with k to the power c, which is a polynomial time algorithm. So now you can guess that smaller the gamma is better. Its closeness to 0 will tell you how fast the algorithm is. So if you can come up with better sub-exponential time algorithms than the known ones for factorization, you can break RSA in an easier way. For this reason, we have to increase our key sizes. So this is why RSA algorithm actually uses huge key sizes, because there are some sub-exponential time algorithms. So let's look at another type of problems. We can define the problems like this in two types: decision and search problem. A decision problem is a problem whose solution or the output is yes or no. So it is a Boolean question. So a question can be like, is this number a prime number? So you can answer yes or no. A search problem is a problem whose solution can be more than yes or no. And again, here is an example. For the search problem, you are given a number n, and you are asked to factorize it. But for the decision problem, you are given the same number, but the question is, this time, is it prime or not? So you might think that these are the same thing. So you might think that I cannot know a number, whether a number is prime or not, without factorizing it. Actually, there are some algorithms which actually solves this decision problem, but it doesn't give you the factorization. So these are two different problems. But of course, if you solve the search problem, this means that you also solve the decision problem. But solving the decision problem does not mean that you solve the search problem. So you might guess that decision problems are sometimes easier than the search problems. And finally, let's give two algorithm types that are generally used in primality testing. We define Monte Carlo algorithms as follows. A yes-biased Monte Carlo algorithm is a randomized algorithm for a decision problem for which the yes answer is definitely correct and the no answer is incorrect with a probability at most epsilon. So there are some algorithms which we call Monte Carlo algorithms, so that when they give you an answer as yes, it is definitely true. And when the algorithm provides you the answer no, it is true with some probability. And these are actually used in primality testing. Another type of algorithms are called Las Vegas algorithms. A Las Vegas algorithm to answer a decision or search problem is an algorithm whose answer is definitely correct if it finishes. So there are this kind of algorithms which runs sometimes forever, but whenever they give you a result, it is always true. So these are some basic definitions about algorithm times and also the definition of the big O notation.